I'm Valentino Vigneri and I welcome you all to this presentation entitled Modified Strut and Tie Model of Head Stud Shear Connectors in Profile Steel Sheeting for Predicting the Post-Cracking Load-Bearing Resistance. Let's first have a look at the contents of this presentation. I will start with introduction and motivation behind our work, followed by the observation of the damage pattern in concrete and the newly developed Modified Strut and Tie Model. After that, I will show you the statistical performance of the resistance function we have derived. And finally, I will sum up the key findings and results in the conclusion section. So, a typical configuration used in the design of steel concrete composite structure is the following. A concrete slab and a downstand steel beam connected via head stud shear connectors, typically welded within the trough of a profile steel sheeting, here shown in the sketch. This solution is particularly used and popular because it is cost effective thanks to the quick installation of the connector and their good structural performance, both in terms of resistance and ductility. Also, there is an extensive literature available in the last decade, which makes this solution and this connector particularly reliable. However, current design rules for predicting the strength of studs given by Eurocode 4 do not take into account the actual mechanical behavior of the connection. There are some alternative mechanical models proposed in the last decades, but they do not accurately predict the resistance of these connectors. In order to overcome this issue, we analyze in detail the failure mechanism and failure behavior of the connection, especially at low displacement. As we can see from this slide, we observed that around a 2 mm slip is so-called initiation of the concrete cone failure, with the crack arising at the edge of the rib, followed by redistribution of the forces and the propagation of this crack across the ribs, leading to the activation of several other resistance mechanisms. This blue part is the main focus of this presentation, and it is so-called post-cracking stage. By translating in equation and in numbers what we observed from the test at around 6 mm, we've been able to develop a new modified strut and tie model displayed in this slide, where the concrete was replaced by the equivalent system of struts in blue. The steel sheeting was considered via tension tie elements. And finally, the stud connector was substituted by a beam element with 1 or 2 plastic hinges, depending on the configuration. In order to solve this structure, we'll first carry out static analysis, aiming to determine the degree of static indeterminacy NS, defined in this equation. Considering the two formal assumptions, the 2 plastic hinges developed along the stud and the tie element D2, which reaches its yield capacity, we can compute the value NS, which is finally equal to 0, meaning that the system is statically determined and can be solved via equilibrium equations. To solve the system, we first focus on the portion OB by considering the horizontal equilibrium equation. The following relationship on the right side of the slab is obtained. Secondly, on the segment, by considering the rotational equilibrium equation around the point A of the entire segment AB, we end up with the second relationship here on the right, where we need to consider additionally the formal assumptions that leads to this equation here, where the bending moment MA and B will be function of the degree of activation of the plastic hinges, so will be function of NY. But we do assume that the full plastic hinges is always developed at the base, so the node B. And we don't have to forget that D2, the tension type D2, reaches its maximum value, so the yielding strength D2Y. With this information, we'll be able to calculate the value P given by this complex relationship here on the right, where we can already distinguish three main resistance components. The first one is the standing bending. The second one is the concrete component, and the third one is governed by steel sheeting. But there are still two unknowns which has to be determined, NY and HS respectively. Former is the degree of activation of plastic hinges, also known as the number of plastic hinges, NY. These plastic hinges are assumed to be always equal to 2 in case of one stud per trough. But when two studs are welded in the same trough, we have lower values of the plastic hinges, as we can see from this plot here. To consider this effect, we have proposed a linear expression where the number of plastic hinges is considered to be linearly proportional to the embedment depth to diameter ratio. Similarly, the location of the upper plastic hinge HS was estimated with the support of numerical simulations. And this relatively complex relationship given here shows a fairly good agreement with the numerical obtained result, as we can see from the bar chart in the slide. So now we have all the information needed to calculate the shear load P, but we do not know the condition of failure because the system is still in equilibrium. But we need to know what is the condition such that the system reaches its maximum capacity. And this condition is exactly the condition of failure considered here as rib punching. This means, in terms of analytical modeling, that the strut C1, representing the bearing forces acting on the shank of the stud, reaches a certain maximum value C1 max. There is again an unknown, and it was estimated using an analogy with reinforced concrete corbel modeling. To make everything clearer, let's see the geometry of these two systems. So on the left we have the hydrostatic shear connection, while on the right we have a typical reinforced concrete corbel. Although there are some differences, I would like to stress the fact that there are some analogy and parallelism between the struts observed in a hydrostatic shear connection and the typical diagonal strut in reinforced concrete corbel. So from these considerations, we have proposed a simplified expression of the maximum value of the strut C1 maximum, equal to a certain effective stress times an effective width L and an effective depth C along the transversal direction. So this parallelism was used mainly to determine the length of L, which is considered to be exactly equal to the height of the compression zone at the rib slab interface. So by doing that, we were able to determine the expression of L given here, and we assumed that the geometrical dimension C is exactly equal to 2D, 2 times the diameter of the stud. And finally, we consider that the effective stress in the concrete is only 60% of the uniaxial compressive strength of concrete, in consideration of the negative impact of the tensile cracks. So all of this information and assumption lead to the following expression shown in the top of the slide. There are still three factors which has to be considered: Kn, Ks, and Kw, which were statistically estimated, and they account for the number of studs per rib, the geometry of the profiles, as well as the welding technology, respectively. So now, in order to check the suitability of this resistance function, we carried out a statistical evaluation of the push-out test results. We're considering a database of 203 push-out tests without transversal load applied and without reported weld seam faults. Also, no test with insufficient embedment length, HSC minus HP, was considered, such that this value would be always higher than the minimum requirement 2D as recommended by Eurocode 4. So from this plot, we can clearly see that there is a good match, a good agreement between the theoretical resistance and experimental resistance. Specifically, the coefficient of variation is relatively low for this type of application. It's about 14%, while the linear correlation factor reaches a value even higher than 0.87. Also, it is worth noticing that the partial safety factor is around 1.26, meaning that this expression can be used for predicting the design strength of studs using a value of 1.25. So, based on experimental evidences, we can say that a novel modified strut and tie model was developed for modeling the post-cracking behavior of studs in profile steel sheeting transverse to the beam. This model was also able to consider at the same time the compressive stresses in the concrete via struts, together with the tension carried by the steel sheeting via tie elements, as well as the bending deformation of the connector, which was replaced by beam elements. Finally, the suitability of the resistance function derived by this model was ensured and checked by carrying out a statistical evaluation, which showed that this formulation is suitable for predicting the design strength of stud with a partial safety factor of 1.25. Nonetheless, there are still some refinement that can be considered. For example, analyzing the distribution of the stresses along the transversal direction, as well as implementing the alternative failure conditions within the model, such as concrete pull-out failure and stud fracture. Thank you very much for your attention.